Hi group, it's Mrs. Schaus. We're going to take a look at section 2.7. I'll let you read through these on your own, but essentially we're going to take a look at some operations of functions, including compositions of those functions. Initially, we're going to start out super simple. Let me try to bring the camera down here a little bit more and adjust the lights there. Super simple, taking a look at sum and difference of some indicated functions. That means that I want to be able to add f and g together to see what I get, and also to subtract those in just a moment. So starting with the addition piece, this is pretty simple. We're going to take the first function, it's a polynomial, right? And we're going to add in the second function. So truly, this is as simple as combining some like terms. I only see one x cubed term, so I'll keep that. 3x squared, but also adding in a 4x squared, that gives me 7x squared. I have just one linear term, plus 5x, and only one constant term, minus 18. So that's pretty basic. How about subtraction? If we do f minus g of x, and of course the order of subtraction matters, so I'm talking about taking the first function and subtracting the second. Do be careful when we say we're subtracting the second function. That means that we're subtracting all of the terms in that second function, so I really have to distribute that negative sign. And now again, I'm just going to combine some like terms. I have one x cubed term, but it's a negative 9x cubed this time. I've got a couple of squared terms, 3x squared and minus 4x squared. That gives me a negative 1x squared. One linear term plus 5x, and one constant term plus 18. Doesn't get much easier than that at this level. Let's move beyond that then. Let's talk about finding the product and quotient of functions. In this case, they also ask us to think about listing the domains. So I want to start out with the product. I want to do f times g of x, which again just means I'm going to take the first function and multiply it by the second. When I multiply across the tops, I get 2x. Across the bottom, I get the quantity x plus 1 being squared. Could I actually expand that out? Of course I could, but I think I'd like to leave it as it is, especially for the moment when I'm thinking about the domain. It's going to be easier to think about the domain if it's in this factored form. What I know is that since this is rational, I need to make sure that the denominator is not going to equal 0. And the value of x that will create that division by 0 is x equaling negative 1. So I want to say it cannot equal negative 1. That is my domain. The domain equals all reals not equal to negative 1. So I'll write it like that. All right, as far as the quotient is concerned, I'm going to take my f of x and divide by g of x. So I'll have 2 over x plus 1, and then that is all over x plus 1. But you folks know that in order to divide with rational expressions, you keep the top fraction and you change to multiplication by taking the reciprocal of the second fraction. So x plus 1 on the top here and x on the bottom there. Now in this case, there's a factor of x plus 1 down below and up above. Those will cancel with one another, and I'm left just with 2 over x. Remember that not only did I want to give this quotient, but I also want to state the domain. So I'm going to say that the domain equals x, that is a real number, but not equal to 0, because the 0 here would create division by 0. However, my fear is that some of you will only look at this piece and you'll pause and say that's my domain. Remember that if this is the initial expression that I start out with, the numerator and also this denominator would not be defined if I allowed the x to equal negative 1 as well. So I want to say it's not equal to 0 and it's not equal to negative 1 either. Okay, find the composition of functions. So this composition, f of g of x, can be written, some of you call this fog. Use this little symbol in the middle. It sort of looks like you know, an O, but it's smaller than that. Kind of reminds me of a degree symbol, but it's centered rather than being written as a superscript, right? And so these two expressions can be read F composed with G, F composite G, the composition of F and G, or F following G. And the one thing I do like about this one is it does remind us that in a sense of thinking about evaluating, or you know, sort of how we're going to manage this, we want to make sure that we're doing G of X first, and then F comes after. So the F is following, taking care of G of X first. Okay. Now, I want you folks to think about finding the compositions of these couple of functions and also giving their domains. So notice that for the first piece here, I'm asking you to calculate F of G of X, and for the second piece, G of F of X. So I'm asking for two different things. For this one, F of G of X, it means that I'm finding F evaluated at, what is G of X? It is this expression, the square root of X minus 3. So I'm really asking you to find F of this expression. What does that mean? It means I go to the F function, and where I see X, I put this in place of it. So that really equals the square root of X minus 3, but now being squared. Okay. If I square that, the square rooting and the squaring undo one another, and I'm left with X minus 3 as a result. So again, to write it out here, F of G of X equals X minus 3. We'll come back to talking about the domain in a minute. All right, let's take a look at G of F of X. So again, that means I'm evaluating the G function for X squared, which means that in place of X in this G function here, so right here, I'm going to put X squared in its place. So I get the square root of X squared minus 3. Let me rewrite that then. Again, that means G of F of X equals the square root of X squared minus 3. Okay, so I've actually evaluated, I found the composition of each of these two functions. I haven't talked about domain yet. Before we do talk about domain, one of the things that I want you to keep in mind is that when we add or when we multiply, the order in which we do those operations does not matter. But when we subtract or when we divide, order does matter. So again, I want you to think about the order of these, you know, functions being composed. If I do F of G, or F of G, if I do G of X, and then follow that with, you know, evaluating that in the F of X function, I get something very different than if I did that in the reverse order. So if I evaluate F of X and then plug that result into G of X, again, I get something quite different. So the order of composition, much like subtraction and division, does in fact matter. Okay, now let's talk about the domain a little bit here. I've pre-written something out because I want you folks to be able to consider a few things about domain. Okay, so let's be careful when we're trying to find domains of compositions. All right, I want you to consider those two functions that we just looked at a moment ago, so our same F of X and G of X. And let's start out with the second one, G of F of X. We said that that was equal to the square root of X squared minus 3. And what I want you folks to know is that I can sort of directly find the domain from what resulted, from what the composition itself looks like in this case, all right? So when I think about finding the domain, what I know is that what sits underneath this square root has to be non-negative. That is, it has to be greater than or equal to 0. Well, in order to solve that, that's a nonlinear inequality. So I'm not just going to add 3 to each side and take the square root, right? Instead, what I want to do is I want to think about factoring it. So here is it written in a factored form. And then I want to use these as interval markings on my number line. We did this in Unit 1, so I'm hoping it's kind of coming back to you folks. And then you're going to test each of these interval pieces to decide if it's part of a solution set or if it's not. And you can see I didn't shade this interior piece here. You see that 0 sets here? If I plug in 0 here, I would get the square root of 3. 0 here, I would get negative square root of 3. And if I multiply a positive square root of 3 times a negative square root of 3, I'm going to get a negative number, which is not greater than or equal to 0. So I hope that makes sense to you. And you could certainly pick another point on either side of those, pieces to decide that those actually are the parts of the domain where this function is defined. Okay. All right. So if I were to then formally write the domain, I would say from negative infinity to negative square roots of 3, including that endpoint, and then also including the square root of 3 to infinity. All right, but now let's consider that first piece that we started with, f of g of x. Remember, we worked through and we said that was equal to x minus 3. All right. Because the composition equals x minus 3, that might make you think that the entire set of real numbers is the domain. Why? Because it's a polynomial function, and we know that polynomials in and of themselves have all real numbers as their domain. But you have to be careful with this. It's not true. Why isn't it true? Because the original function g of x is only defined when x is greater than or equal to 3. I mean, think about the original function. It was g of x equals the square root of x minus 3. If we put some real numbers in there, ones that are not greater than or equal to positive 3, let's say we put in 0, that would give us a square root of a negative number, again, not defined in the set of reals, right? So we need to make this restriction on the domain based on the original function. Okay? So sometimes you do have to sort of inspect the original functions. Okay? Since the domain of f of x is all reals, the entire domain is just limited, as I mentioned a moment ago here, to x's that are greater than or equal to 3. You do have to be careful. Sometimes you could end up with a situation where we have to further look at f of x. Maybe f of x wouldn't have all reals as its initial domain as well. Really, when it comes to domains of a composition, it is, first of all, in order to be an element of the domain of the composition, it must be an element of the domain of the first function. So in this case, it would be, of g of x. But then also the outputs of g of x must be things that define the second function, f of x. Okay? So I hope that makes it a little bit more clear, but do be careful when you're trying to find those domain pieces, okay? All right. I want to also have you folks look at, get my papers in the right order here, the same two functions, but this time I'm asking you to calculate f of x. When we compose a function with itself, that actually has a special name. It's called an iterate, or if we repeat that process, we call it iteration. And there are some real applications geared around the idea of iteration, like involving population and some other things. So perhaps you'll run across it. But I do want to compose the function f with itself. So that means that I'm finding f of x squared. And what does that mean? Well, it means that in the original f of x function where I see x, I'm going to put an x squared. So I would actually have x squared squared, or x to the fourth. Again, I'll rewrite the statement. F of x equals x to the fourth power. All right, and then I also want you to think about finding a composition where we're evaluating at a specific number. So in this case, I want to find out what g of 12 is first, and then I'm going to find g of that. So what's sitting in the interior here is this function evaluated at 12. Well, let's see, that's really g of 12 minus 3 is 9. The square root of 9 is 3. So we're really finding g of 3, which means that I go back to this function again, and I plug in 3, and I get the square root of 0, or just 0. So g of 12 equals 0. Remember that g of 12 was 3. But then evaluating the function again at 3 gave me a result of 0. That's what this statement means. Okay? All right, now I want to talk a little bit about the process of decomposing a function. Decomposing a function sort of means like we're working in reverse. That is, they're giving us the function after it's already been composed, and they want us to say what the two original functions were that created it. Now, be careful, they're asking us to find functions f of x and g of x so that when we do g of x first, following that we'll apply f of x. We'll get this as a result. Okay? So I think the easiest way to probably do this is to just probably pick some things and give it a try. I noticed that there is something that's cube rooted here. And then I also noticed that there's some expression that has 1 subtracted from it. So, maybe I'll try something like, what if I let g of x be the cube root of x? And then what if I let f of x equal x minus 1? Now, sometimes folks will, give this a try and they'll reverse the order of them accidentally. So once I think I found what works, I should just, after I've guessed, I check. So I want to calculate what is f of g of x and see if I really get this capital F of x that I'm looking for. That means I'm going to evaluate f at the cube root of x. And what does that mean? It means that I'm going to go to my f of x function that I just wrote, and this is going to go in place of x. So I get the cube root of x minus 1. And that, in fact, equals our capital F of x that we were looking for. So this little f of x and little g of x do, in fact, give me the capital F of x that I was looking for. All right, let's take a look at a couple more of the decomposing problems. So, whoops, sorry about that, bumped the camera. So again, here I'm given capital G of x, here's the function, and they're asking me to find two functions, little f of x and little g of x, such that this is the result when I perform this composition. Let's see, and perhaps there's more than one way to actually work through this. I could say little f of x equals 2x, and little g of x equals x squared minus 6. That whole quantity, x squared minus 6. Now, if I do that, then when I calculate f of my g of x is x squared minus 6, remember that means that I go to this f of x function, and where I see the x, I put this in its place. So I would end up with 2 times the quantity x squared minus 6. Ah, that works. So here is one such possibility. Is there another? Well, let's see. I could say, I'm going to say option 2 here. Option 2. I could say that f of x equals, let's do 2 times the quantity x minus 6, and g of x equals x squared. Now, if I'm claiming that that's true, remember I should once again be able to show that if I do f of g of x, well, g of x is x squared. So if I do f of x squared, I should get back to this original function, do I? Well, in this little f function where I see the x, I'm going to put x squared in its place. So 2 times the quantity, x squared minus 6. Yes, in fact, that works again. So there is another option of two little functions, f of x and g of x, that will give me this composition. The easiest way to, I think, sort of explore these is truly just to try some things. I mean, I noticed that there was a power here, so allowing one of my functions to equal just x squared seems pretty reasonable, all right? What I want you folks to do is understand that I'm not going to allow you to use what I'm going to call the simple case. The simple case is where I let g of x equal just x itself, and then f of x equals the same thing as the composed function. So you won't be able to give me that as a response. But anything else, any two other functions that are not, involving one of them just being x itself, the g of x in particular, then as long as it really checks, then that would be an appropriate answer, okay? So for this one, again, I'm looking for little f of x and little g of x, so that when I compose them, I end up with this expression. That means as one of my options, I could say f of x equals the absolute value of x, and g of x equals the quantity 3 minus 1/2 x. Let's compose that and see what we get. F of g of x is 3 minus 1/2 x. If I evaluate that, again, that means that I'm plugging this in place of x in the f of x function. So I get the absolute value of 3 minus 1/2 x. And yes, in fact, that equals the h of x that we were looking for. So that is one possibility. Are there others? Perhaps. I'll let you think about that. All right, now, the very last thing that I want to do with you folks is take a look at an application. It says, a spherical balloon is being inflated. The radius of the balloon is increasing at a rate of 1 centimeter per second. We're asked to do three things. Find a function that models the radius as a function of time. Find a function g that models the volume as a function of the radius. And then finally, they're asking us to consider a composition, but they want to know what the composition really, what does that new function represent? So let's kind of dig in here. Again, if the balloon is being inflated in this way, the radius of the balloon is increasing at a rate of 1 centimeter per second. They want f, this function that we're going to call f, to model the radius as a function of time. Well, if it's a function of time, we have to call it f of t, right? T is going to be our input variable. And that radius is increasing at a rate of 1 centimeter per second. So I could say 1 times t. But you know, 1 times t is just t. So I'm going to write f of t equals t. If 1 second goes by, we get 1 as an output. If 3 seconds have gone by, 3 is an output. Okay. Part B says find a function g that models the volume as a function of radius. So I'm going to write g of r because, again, we're using radius as the input and we're wanting to find volume. So you might, if you were working on your own here, have had to go back and look up the volume for this spherical balloon. And then you'd be able to tell me that the formula is 4/3 pi r cubed. Okay? Remember that that's representing volume of this spherical balloon. All right, now, we're asked to find the composition g composite f of t, or composed with f of t, right? So that means we're really finding g of, well, what did f of t equal? Remember, it equaled t itself. So now, in order to evaluate that, I just have to put t in place of r. So I'm going to write that equals 4/3 pi t cubed. And what does this tell me? Well, go back to the original functions and think about what they represented. This first one represented the radius as time changed. This next one represented volume based on radius. So this now represents volume based on time. So I'm going to write down this equals volume as a function of time. Yeah, think about it. If you're blowing it up, the balloon gets larger and larger. It's not only the radius that's changing there, it is the volume that's changing as well, right? So this expression representing that volume, if I plugged in, 2 seconds or 8 seconds or however much time has gone by, I could simplify this expression and I would have the volume of the balloon. Okay, well, as long as it doesn't pop, that is. All right. So I think we've covered everything we need to on our operations, composition, including thinking a little bit about the domain and application. I'm going to assign some exercises from the section, give those a try, and I'll talk to you folks soon. Make it a great day.